Hello everyone, you are listening to Professor Rajendra Tadakhe, Department of Mechanical Engineering, Marathwada Mitramandals College of Engineering, Karvenagar, Pune. I welcome you all to the series of lectures on the theory of machines 1. This is our 8th lecture on the acceleration analysis by relative velocity method. So in today's lecture, we are going to have the one problem for the acceleration analysis by using a relative velocity method. So let's start with the problem statement. So here it is the problem statement. We are provided with the slider crank mechanism, and for this we have to perform the velocity analysis and the acceleration analysis. So whenever it is asked to calculate the acceleration of any link or any point on the link, then before we proceed further for the acceleration analysis, velocity analysis is the prior and the essential step. So let's start with the problem. An IC engine mechanism as shown in the figure, in which the crank AB rotates at 600 rpm. The length of the crank AB is 0.5 meter and the connecting rod is 2 meter long. When the crank is turned 45 degrees from the inner dead center, we have to find velocity of the piston P, angular velocity of the connecting rod dP, then velocity of point D on the connecting rod, which is at a distance of 0.5 meter from B. Then the last point is we have to find the acceleration of point D and angular acceleration of the connecting rod, and this is the given figure. So let's start with the solution. So first of all we have to write the given data. So the speed of the crank is given, which is 600 rpm. Then length of crank is given, which is 0.5 meter. Then length of the connecting rod is mentioned, which is 2 meter. So in the step 2, we have to put the things which we have to calculate. So we are asked to calculate the angular velocity of the link PB, then velocity of the piston, which is Vp, then velocity of the point D, which is on the connecting rod at a distance of 0.5 meter from B. The next one is we have to find the acceleration of point D, again which is on the connecting rod at a distance of 0.5 meter. And finally, we have to find the angular acceleration of the connecting rod. So these are the things we have to find. Now the step number 3 is the configuration diagram. So now we have to draw the configuration diagram. So to draw the configuration diagram, we are using a scale which is 1 centimeter as 0.5 meter. Means 1 centimeter line will represent a distance of 0.25 meter. So accordingly we have to draw the configuration diagram. So configuration diagram means we have to draw the slider crank mechanism with the given dimensions in the problem statement. So why we have chosen this scale 1 centimeter as 0.25 meter? Because the length of AB, that is crank, is given as 0.5 meter. So it is again difficult to accommodate this 0.5 meter on the sheet. Then the connecting rod is 2 meter long. So again, if you think of this dimension, then again it is too large to accommodate on the sheet. So what we are doing? We are choosing a scale that 1 centimeter is 0.5 meter. So 0.5 meter will be equal to 2 centimeter and 2 meter will be equal to 8 centimeter according to this scale. So let's start with the configuration diagram. So here it is the configuration diagram. So in the configuration diagram, so first of all what we will do, we'll try to understand how to construct this configuration diagram. So now fix this point A. So the angle AB with the horizontal line is 45 degrees. So this is a 45 degree angle with the horizontal or with the stroke, or we can say with respect to the IDC. So this is crank AB. So length of AB is known, the angle is known, so we'll get the point B, and we have to draw the straight horizontal line through point A. Now we have to locate the point P. So once we locate the point P, then we can draw PB. So to get this, what we have to do, we have to take a distance in the compass which is equal to the BP, and we have to keep one point at B and mark the arc on the line of stroke. So we'll get point P, and the distance of point D from B is 0.5 meter. So according to this scale, 0.5 meter means it is 2 centimeters. So at a distance of 2 centimeters, we have to mark the point D from B. So once the configuration diagram is done, we have to proceed further for the velocity polygon. So again, the velocity polygon we have to construct as discussed in the earlier lecture. So already we have studied about the velocity polygon. So in this lecture, specifically we are going to concentrate on the acceleration polygon. So construct the velocity polygon as discussed earlier. So I will explain it briefly. So let's start with the construction of the velocity polygon. So again, to start with the construction of the velocity polygon, what we have to do? We have to look for the input link. So here input link is AB, for which the RPM is given, which is 600 RPM. So by using this, what we can calculate? We can calculate its angular velocity. Once the angular velocity is known, then we can calculate the linear velocity of point B or for the link AB. So once we get this, then we can draw a one velocity vector which will represent the velocity of point B with respect to A. So that is going to be an absolute velocity of point B with respect to point A. So let's start calculating the linear velocity of point B. So angular velocity of the link AB is, by using this formula, omega is equal to 2 pi n by 60. So n is given, which is 600 RPM. So put the corresponding values. So we'll get omega AB is equal to 62.831 radian per second. So by next step is calculate the linear velocity by using V is equal to R omega. So put the corresponding value. So if we put these corresponding values, we will get R and omega, and will help us to get the value of linear velocity. So the linear velocity of point B is 31.415 meter per second. So now we are having the linear velocity for the point B. So let's start with the construction of the velocity polygon. So here the point A is fixed. So take a point in the space. So before that, we have to consider the scale for the velocity polygon, because here also this, if you look at the magnitude of the velocity of point B, it is 31.415 meter per second. So we'll take 1 centimeter will represent a velocity, linear velocity of 6 meter per second. So according to this scale, we have to draw the velocity vector of the link AB. Now the linear velocity vector for the link AB is perpendicular to link AB. So take one point which is called as the pole of the velocity polygon. So, and this pole will represent all the fixed point in the configuration diagram. But for this configuration, we are having only point A as a fixed point. So name this point as small a. So one point is important. So whenever we are drawing the velocity and acceleration polygon, we have to make the use of all the relevant or corresponding small letters. So let's say here we are having the capital A, so use small a. Here we are having this capital B, so use the small b. So let's draw the velocity vector for the link AB, which will be according to this scale. So VB is 31.415 meter per second. So draw the perpendicular to the link AB. So here we have drawn the velocity vector of the link AB, or which represent the linear velocity of point B with respect to A. So this point is B, and this is representing the velocity of point B, or we can say it is VBA, which means the velocity of point B observed from A. But as the point A is fixed, so we can write it as only VB. Okay, so after this, what we have to do is, we know the direction of the linear velocities for the link BP and the linear velocity of the piston P. So what we have to do, we have to draw, we know the position of B. So what we will do, we'll draw the linear velocity vector direction, not magnitude, because what we know for the velocity vector of link BP, only direction, we don't know the magnitude. So draw a perpendicular, and we know the linear velocity vector is perpendicular to link BP, or linear velocity or tangential velocity is perpendicular to the link BP. So what we have to do in the next step, we have to draw the perpendicular to the link BP through point B. So here we have drawn the perpendicular to the connecting rod through point B. Now go to the slider. Now slider is having again a linear motion. So this is rotating in the clockwise direction. So the piston will travel towards right hand side. So we have to draw the velocity vector in that direction. So, and this is passing through point A. So here we are having point A. So if I draw the velocity vector to the left hand side, of the point A, then it is not going to intersect to the linear velocity vector of the link BP. Then we will not get the magnitude, or will not get the point P. So in order to get the location of the point P, what we have to do, we have to draw the linear velocity vector of the piston in such a way that it will intersect to the direction of linear velocity vector of connecting rod. So here it is the linear velocity vector of the piston or the slider. So the point of intersection of both the vectors is nothing but the point P. So now this is representing, the BP is representing the linear velocity of the connecting rod, and this AP is representing a linear velocity of the piston. So this is velocity of point P observed from B, and this one is velocity of the piston observed from point A. Now in the next step, what we have to do, we have to locate the point D. So this point D is dividing the BP in some ratio. So in the velocity polygon as well, it will divide the vector BP in the same ratio as it divides the connecting rod BP. So to locate the point D, we'll use this. So this means that the small d will divide the vector BP in the same ratio as it divides the connecting rod in the configuration diagram. So according to this, for this we have written this formula, that BP upon BD is equal to small bp upon small bd. So in this we have to put the corresponding values now, or you can simplify for BD. So BP. So BP means this length you have to measure, this vector length you have to measure. Then BD, P to D is distance is known, which is 0.5. Then BP, again it is the length of connecting rod, is also known. So put the corresponding values and get the value of small bd. So which will help you to locate the point D in the velocity polygon. So BD is equal to 3.7. So 3.7 is the length of vector BP, which is measured from the velocity polygon and multiplied by 0.5 by 2. So here it is the distance of point D from point B, which is 0.925 centimeter. So now what we know, the location of point D, which is at a distance of 0.925 centimeter from B. So here it is the point D we have located. Now to get the velocity of this point D, and this point D we have located according to this statements. and we get the value of BD as 0.925 centimeter. So according to the same, we have marked the point D on the vector BP. Now to get the absolute velocity of this point D, what we have to do is we have to connect this point with the fixed point A. So this is the velocity of D, or absolute velocity of point D. Now the next part is, here we have completed with the velocity polygon. So the next part remains is we have to calculate the velocity of piston and velocity of point D from the velocity polygon. So later on we will calculate, or we will move further for the calculation of the accelerations for the different links, or for which it is asked. Now in this, to get the velocity of piston Vp or angular velocity of the link PB, what we have to do? Where is the PB? Here it is the vector PB, which is representing the linear velocity. So measure this length, use the formula V is equal to R omega. So we'll get the omega from this, and which is asked. So we'll start with the angular velocity of link PB. So from the velocity polygon, the VPB is equal to the length of vector BP. So it is 3.7, and into the scale which we have chosen. So what scale we have considered for the velocity polygon or velocity diagram? It is 1 centimeter is equal to 6 meter per second. So that is why it is 3 into 6. Then VPB is equal to the multiplication of these two quantities is 22.2 meter per second. So it gives the linear velocity of the connecting rod at the given instant. But what we are asked to calculate? We are asked to calculate its angular velocity. So we use the formula V is equal to R omega. So VPB is equal to PB into omega PB. So put the corresponding values in this. So VPB is 22.2, PB is 2 meter, and omega PB is to be calculated. So we'll get the omega PB is equal to 11.1 radian per second. So that is the final answer for the angular velocity of the link PB or connecting rod. So to get the velocity of piston Vp, what we have to do? Just measure the length of this vector AP or PA and multiplied by scale. So velocity of piston Vp is equal to vector AP is equal to 4.4 is the length which is measured from the velocity polygon, and multiplied by 6, which is the scale we have chosen, which is 1 centimeter will represent the 6 meter per second linear velocity. So Vp is equal to 26.4 meter per second. So what we are left with now in terms of velocity, we are left with the velocity of point D. So what we have to do to get the velocity of point D with respect to point A, measure this length AD and multiply by scale. So VD is equal to vector AD. So 4.8 into 6. So 4.8 is the length of AD. So here is the velocity of the point D, which is 28.8 meter per second. So these are the final answers for the velocities. Now what we are left with? We are left with the acceleration of the point D and angular acceleration of the connecting rod. So once we complete the velocity polygon, and if it is asked for the acceleration, so we have to proceed further for the acceleration analysis. So let's start with the acceleration diagram. So before we start with the acceleration diagram, we already have discussed what are the different types of the components are there for the given links. So according to that, we have to prepare one table. So in this table, what we are having is we are having the name of the link, then length of the link, which we call it as a radius, then velocity of the link, which we calculate by using the standard formula, which is V is equal to R omega, then acceleration of the link. So in case of the acceleration of the link, we are having the normal component and the tangential component. Okay, so we will try to understand this table. So in the name of the link, how many links we are having? The 3 links. We are having link AB, that is crank, which is rotating at a uniform speed. Then it is BP is connecting rod, and slider is P. So length of the link is for connecting rod is 0.5, and for crank it is 0.5 meter, and for the connecting rod it is 2 meter. So slider is not having any length, so we have not marked or not written its length. Then the velocity of the link. So to get the velocity of link AB, so being an input link, so already we have calculated its linear velocity, which comes 31.415. Then for the BP, what we have to do? Just measure the length of the vector BP and multiply by scale. So we'll get the velocity of the link as 22.2 meter per second. And for the slider P, so again we have to perform the same procedure. We know the location of the point A and we know the location of point P. So measure the vector length AP and multiply by scale. So we get 26.4. So I think till this step it is very easy. Just we have to take the help of velocity polygon and the given data to calculate the linear velocities of the different link. Now coming to the acceleration of the link, first of all we will try to understand the two different components. So already I have explained in the earlier example, but just we will revise it. What are the two different components of the acceleration are there for the given link? So basically we are having the normal and the tangential component for the given link. Okay, so when the link is rotating at the uniform speed, so in that case what happens? It is not having any kind of angular acceleration. So in that case the tangential component of acceleration becomes 0, and in that case the link is having only normal component of acceleration. So let's start with the one by one. So first we are having the link AB. So AB is the input link. So now in the problem statement it is mentioned that crank AB is the input link which is rotating at the constant speed or the uniform speed. So that is why it is not going to have the tangential component of acceleration. As the link is having uniform speed, therefore its angular acceleration is 0. That is why the tangential component is 0, because the crank rotates at uniform speed. But it is having a normal component which is equal to v square by r. So now v means its linear velocity, which is 31.415, divided by r. R means the length of the link, which is 0.5. So 31.415 the square divided by 0.5. So we'll get 1973.804 as the magnitude of the normal component of acceleration for the input or the crank. Then moving to the connecting rod, we know its length as well as the velocity of the link is known, linear velocity. Then 22.2 square divided by 2 will get 246.42. Now for connecting rod BP, we are having the normal component as well as we also have the tangential component. But we don't know the magnitude of the tangential component of acceleration for the connecting rod. But what we know its direction, and it is perpendicular to the BP, or what we can say, it is parallel to the velocity vector. Okay, so let me clear one thing about the directions of the normal component and the tangential component of acceleration. Normal component of acceleration is always parallel to the link, and the tangential component is always perpendicular to the link, or we can say in other words that tangential component of acceleration is parallel to the velocity vector in the velocity polygon. Then coming to the slider, now the slider is having normal component of acceleration as 0, provided the slider is sliding over the straight line or sliding along a straight line. So why it becomes 0? Because when the slider is moving along a straight line, so in that case the value of r is infinity. Means we assume that, or it is considered that when the slider is moving along a straight line, in that case the radius of the circle is infinity. That is why the normal component of acceleration becomes 0 in case of the slider when it moves along a straight line. Then for the tangential component of acceleration of the slider, we know the magnitude. We don't know the magnitude, but we are aware of the direction, and which is parallel to the line of stroke of the piston. I hope you have understood this table. If you have not understood any part of this, so you can comment in the comment box and I will resolve those queries. Now we'll start with drawing the acceleration polygon. So again, to start with it, what we have to do, by looking at the magnitude of this, we have to choose a particular scale and then we have to proceed further. So the scale for the acceleration diagram we have chosen that 1 centimeter will represent a acceleration of 250 meter per second square. And this is the configuration diagram. So you need not to redraw the configuration diagram. So once you draw it, that is enough. But just I have taken here for the sake of reference. Okay, so you can continue with the same line, because when you draw in the examination or when you solve the problem of the acceleration or the velocity analysis, so entire thing will be on the half empirical sheet. So you need not to draw the configuration, or you need not to repeat the configuration diagram while drawing the acceleration polygon. Just in the initial in the starting of the solution, if you draw it, that is more than enough. Now we'll start with the acceleration polygon. So how many fixed point we are having here? 1. Exactly, we are having 1 fixed point. So that same as in case of the velocity polygon, we have represented all the fixed point by the single point which is called as the pole of that velocity polygon. So exactly the same process we have to follow here. We have to represent all the fixed point from the from the configuration diagram. We have to represent all the fixed point from the configuration diagram with a single point in the velocity polygon. So this is the point which is called as the pole of the acceleration diagram. So this is point A. Now we have to draw the normal component of acceleration of the crank. So we know the direction and magnitude as well. So according to this scale, so 1973.804 divided by 250, so we'll get some length. So that is nothing but the length of the vector which will represent the acceleration of the link AB, or the normal component of acceleration of the link AB. So as discussed, this normal component of acceleration is having an direction parallel to the link AB. So, and the magnitude we have as 1973.804. So length will be this value divided by 250. So here it is point B, here it is point A. So this vector is representing a normal component of acceleration of the link AB, and its tangential component of acceleration is 0 because this AB is rotating at uniform speed. So this vector is representing a normal component of acceleration for the link AB. So as the tangential is 0, tangential component of acceleration is 0, therefore the total acceleration will be equal to the normal component of acceleration. Now we are having the location of point A and point B. So with respect to this, we can construct the acceleration diagram further. Now consider the link BP. So for BP, again it is a connecting rod. So it is having a 2 component of acceleration, normal and the tangential. For normal, we know the magnitude, and for tangential we know the direction. So sorry, for the normal component we know both its magnitude as well as direction, and in case of tangential component of the connecting rod we are aware of only direction. So according to that, we will try to draw the velocity, we'll draw the acceleration components for the link PB. So first we'll draw the normal component. So according to this scale, 1 centimeter is equal to 250 meter per second square. According to this scale, approximately this normal component will be represented by the length of 1 centimeter vector. So here it is the vector which is representing a normal component of acceleration of the connecting rod. So here it is point B, and this is going to be your point. Okay, so this is the normal component of acceleration for the connecting rod. Now, the tangential component of acceleration will be perpendicular to the link or perpendicular to this normal component, because this normal component is parallel to the link. So draw the direction of the tangential component of acceleration for the connecting rod or for the link PP. So here we have marked its direction. We don't know the magnitude. Okay. Now we will get point P on somewhere here. So for the slider, we don't have the normal component, but we are having only the tangential component, and its direction is along the line of stroke. So we have to draw the line or the vector through point A in the velocity, not velocity, in the acceleration polygon. So if we draw in this direction, so it is not going to intersect to the direction of the tangential component of acceleration of the connecting rod. So what we'll do, we'll draw in such a way that it will intersect to the tangential component of acceleration of the connecting rod. This is one way to understand the direction, or other way is this one, that is link AB crank is rotating in the clockwise direction. So the piston will move towards point A. So here we have to draw so in this direction, that is towards right hand side from the point A, we have to draw the vector which will represent the tangential component of acceleration, which is equal to the total acceleration of the link P or slider P. So at the intersection, this point is P and this point is P dash. Now to get the total acceleration of the connecting rod, we have to connect this B and P. So we have connected these 2 points, and this is representing the total acceleration of the connecting rod. So once we get the total acceleration of the connecting rod, we have done with the acceleration diagram. Now we have to proceed further for the location of point D on the vector BP. So the point D will divide the vector BP or PB in the same ratio as it divides the length of connecting rod. So in this way we will locate the point D on the vector PB. So to locate the point D in the acceleration diagram, so PB is equal to BP is equal BP upon BD is equal to BP upon BD. So we have to get the value of BD. So according to that, we'll put the values, and the value is 1.425 centimeters. So from a point B, the point D is at a distance of 1.425 centimeters. So from this, mark a distance of 1.425 centimeter and locate the point D. And so here it is the point D. Now to get its acceleration, total acceleration, so connect it with point A. So now we know the total acceleration of point D. So if we measure its length and multiply by scale, we'll get its total acceleration or acceleration of point D. So next step is the calculation of the linear and angular acceleration for the various links. So which we can calculate by measurement from the acceleration diagram. So already we are having the acceleration diagram. So to get the acceleration of point D, what we have to do? Just measure the length of vector AD multiply by scale which we have chosen for the acceleration diagram. So we'll get the answer for the acceleration of point D as 1750 meter per second square. So this is our one of the answer. Then to get the tangential component of acceleration for the connecting rod, because why we are calculating the tangential component of acceleration of the connecting rod, because it is asked in the problem statement to calculate the angular velocity of the connecting rod. So in order to get the magnitude of the angular velocity of the connecting, not angular velocity, the angular acceleration of the connecting rod, we need to find the tangential component of acceleration of the connecting rod. Because if you look at the formula of the tangential component of acceleration of the connecting rod, then it is equal to R alpha. So this alpha is nothing but the angular acceleration. So AT is equal to R alpha. So now we know the value of tangential component of acceleration, which is represented by the vector P dash P. So measure the length of the vector P dash P, multiply by the scale, then we get the answer as 1375 meter per second square. Then AT is equal to R alpha or RA. So this A stands for the angular acceleration. So AT is equal to BP, AT BP is equal to BP into alpha BP. So this we have to calculate. So we know the value of this tangential component of acceleration, which is 1375. BP we know, which is 2 meter. So put the corresponding values, and finally according to this we get the connecting rod angular acceleration is 687.5 radian per second square. So this is our final answers. So this is how we perform the acceleration analysis for the mechanism. So here it completes the solution for the slider crank mechanism for velocity analysis and the acceleration analysis by using a relative velocity method.